Recording in
math
progress.
for computer science students.
Yeah, I mean, he was just like, guys, there's somewhere I can sit down and do some work.
And joined the applied math, like, office.
Yeah.
Yeah.
You're on my webpage?
Yeah, I gotta introduce you.
Oh.
Oh, but I can't get your PDF, your CV.
Yeah.
Yeah. I Googled you and I got your,
Oh, I see.
I got your promotion for.
יש שני חדרים של מסלולים של graduate students. יש גם עוד אחד, כמה במשרד שלך, זה actually all בחדר אחר זה אני סטודנטית שהיא גם סטודנטית שלה, ג'ונס הוא סטודנט של אף אחד.
Yeah, what you wanted us to tell you. And when you watch my laptop, all the good of that.
Yeah.
Vladimir may have decided he didn't need to come. I said it's about 0 communications and some combinatorial thing. He said.
Robbie said he will on Zoom.
What?
Robbie said he will be on Zoom.
Robbie's gonna be on Zoom. Okay. Is there anybody else? Yeah, it is 4 o'clock. Oh, I'm here. I got your intro. This is the second Friends of Anna talk. This is the second talk in the series of the Friends of Anna. Part of applied math. Anna doesn't have too many friends, so this is it for the end of the talk. The end of the series, Vladimir says he only has enemies, not friends. So I've got 2 friends. So I am thrilled to have Seth Pettie come talk again. Actually, he spoke several years ago, and it was a very popular talk. So Seth is currently a professor of is it still electrical engineering and computer science?
Oh, yeah.
Excellent, at the University of Michigan. He has been there since 2006. Before that, he was a postdoctoral researcher at the Max Planck Institute in Saarbrücken, Germany. He received his PhD from the University of Texas at Austin in 2003. And he is going to talk about the Pardosh conjecture for 0-1 matrices.
Thank you, Anna. Okay, so this is joint work with Gabor Tardosh. So how I got started with working with Gabor was I was doing a sabbatical in Israel, and then I had to leave in a hurry. And at this point, you know, someone was living in our house, so we couldn't go home to our house. My wife went back to live with her, you know, her mom, and then I said, I'm going to Europe. So I did a reverse lookup to see who had a 2 million euro ERC grant that they had trouble spending. And Gabor had one. And I knew Gabor and I liked Gabor a lot. So I'm like, I'm going to go to Bucharest. So I email him up and I say, hey, can I come stay for like a week or two? And he's like, sure, no problem. And that's how we got started. So that's the story. Okay. So yeah, so the subject of the talk is basically this extremal function for the number of ones you can pack into a 0-1 matrix, an n by n 0-1 matrix that avoids some pattern P. Okay, so it's best explained with an example, of course. So you know, here's a 0-1 pattern P. All the blanks are zeros, and I'm going to attempt to convince you that this extremal function here is at least n log n in this case. Okay. So how could I do that? I could come up with some example matrices that, you know, show you can actually pack this many ones into the matrix and still avoid this pattern. So the construction is you put ones along the main diagonal here, and all the diagonals that are off from it by power of 2. Okay, so the first, the second, the fourth, the eighth diagonal, they're all ones. Okay, and you know, you could color code these ones here if you wanted. You could, you know, make these 3 yellow, and if you ever saw 3 yellow ones in that kind of triangular configuration, then this red spot here would have to be on or below the main diagonal, which means the purple one is definitely below the main diagonal, and therefore it can't be a 1. Okay, and that's the entire argument. So, any questions on the definition? Because I just did it by example. So we're not talking about contiguous subjects. Okay. Okay, so there's lots of applications for these things. They started off in geometry. I showed that you can use them to analyze data structures. I'll get to that in a bit. They were used to prove some big theorems in enumerative combinatorics and to develop some stuff in graph theory. So the definition of twin width basically uses this kind of machinery. So you know, this talk I'm going to spend, I guess, the first half just sort of surveying what you can do with these matrices and some of the history of this problem. Okay. So here's one of the original geometric applications. So if you were, you know, staring up at this arrangement of lines from below, what you'd see is some funny jagged surface where you see some lines and some other lines and some other lines. And this this lower envelope, which is the pointwise minimum of these line segments here, has several breakpoints. Okay, and you could express how sort of complex this this lower envelope is by giving every line, you know, a name, let's say A, B, C, D, E, and then just writing down what the line segment is that you're looking at in each segment of the lower envelope. Okay, and this sequence here, this would be called a order 3 Davenport-Schinzel sequence, and what that means is that you'll never see the pattern ABABA in this sequence anywhere, because that means that the lines A and B basically were bent. At least one of them was bent. Okay. So what is it? How can you turn this into a 0-1 matrix problem? Well, you can give each letter a row. So each line gets a row. And then you could chop this sequence up into blocks where all the letters are distinct. So you could say AB is a block, AC is a block, AD is a block, you know, ADC is a block, ADCB is a block, and so forth. So you give a column for every block, you give a line for every row, and you put a 1 there when that symbol appears in that block. Okay, and just as you can show that this sequence is AB free, it also avoids this this pattern here Q. Okay, and the extremal function for this pattern is a little bit superlinear. It's n times inverse Ackermann. This was shown back in the 80s, but this is sort of one genre of things that you can do with these 0-1 matrices. So here's another geometric application. This is an old question. If you put some points in the plane, how many pairs can you arrange to have be at unit distance? Okay, and this is, as far as I know, still more or less, no progress has been made since the 80s. So there's a very, loose upper and lower bounds right now. And then you can ask more specific versions of this question, like suppose you had to arrange your endpoints in convex position, then how many unit distances could you get out? And here you can actually use zero matrices to get a pretty good estimate on this bound. That this is the same pattern we saw before, that it's at most n log n. Okay. And the argument for this kind of thing, this was shown by Ferretti in the 90s, who basically came up with this whole, 0-1 matrix way to model the problem. Okay, so how does the proof basically go? You show that in your convex arrangement, it's always possible to draw a line through your convex arrangement that cuts a constant fraction of the unit distance pairs. Okay, so we'll call everything below the line rows, we'll call everything above the line columns, and now we'll stick a 1 in the corresponding thing in the matrix wherever you see a unit distance. So if you have a point, let's say the ith row in the jth column, you'll see a 1 if they're at unit distance. Okay. So what's the problem here? So if you did see this pattern, what does that mean? You see two points below the line and 3 points above the line, and they have unit distances that are in this arrangement here. Okay, so geometrically, what that means is that, let's say these are your 2 rows and these are your 3 columns. And if all 3 of these were at all these, 4 pairs here were at unit distance, then this 5th one would just have to be in the convex hull of the others, and therefore it's not in convex position. So therefore this matrix would avoid this pattern. Okay. All good? Okay. So here's one that I came up with about 15 years ago. You can use these matrices to analyze data structure. So here's a very, very simple classic data structure. It's called union find. So it supports 2 operations. You have a bunch of disjoint sets at any particular time. You can point at 2 of them, say A and B, and you can say replace A and B with their union. Okay, and then you can also point at an element in one of the sets and say, give me a representative element in that set, so I can, if I give 2 elements, if they have the same representative, then I know they're in the same set. Okay, so the way you represent this data structure is a rooted tree. Every set gets its own rooted tree. And when you perform a find, let's say on this thing here, the representative is going to be the root. So how do you get to the root? You crawl up to the root and you return the root. And to make sure you don't waste this time that you spent doing all this crawling up the tree, you compress this path here. So, after doing a find on the blue element here, everything now points to the root. And this obviously doesn't change the set system, but it does make more future finds more efficient. If you perform a find over here on the red element, then it looks like that. Whenever you perform unions, you're just linking trees. So if you perform 2 unions, you could link these trees up. And then if you performed a find on the blue element again, it would look like that. And if you performed a find on F, it would look like this. So forth and so on. Okay, so the question here, the analysis question here is, if you do a certain number of unions and finds, what's the total length of all the path compressions? Because that's the time. And the way you can model this problem as a 0-1 matrix is just to say, well, one axis is time. One axis is, I'm going to list out all the elements in my data structure in some special order. The special order here is post order. So I imagine I performed all the unions at the beginning, and then I list the elements in that tree in post order, and then that's their fixed order here. Okay, and I'll put a 1 in the matrix whenever operation number I touches element number j. Okay. So you can show that this matrix avoids, in fact, this very same pattern, and therefore you're going to get an n log n upper bound on the length of all path compressions. Okay, it's a very simple argument to see that it can't have this. There's no real calculations involved. You just have to confirm that it doesn't show up here. Okay, and this in fact matches an n log n lower bound, so it's tight in this particular case. And this is by Michael Fisher, who still at Yale, still alive?
Yeah, still alive.
Okay, so Michael Fisher, around here somewhere. And how does the argument go? Okay, So the argument goes like this. So if this were to appear in the matrix, what this means is that, you know, there were two operations, operation I at time I and J at time J, and operation I touched A and C, and operation J touched A and B later on. And how could that possibly happen? Well, the only way you can get this arrangement here is because of the post order is A is a descendant of B, which is a descendant of C. Okay. So if I came along and touched A and C, that means it changed their parent pointer. So after the ith operation, the picture looks like this, where A and C are now unrelated, and therefore A and B are unrelated, and therefore it's impossible for any operation to come along and touch both A and B. It can only touch an ancestral path. Okay, and that's the end of the proof essentially. So this method gives you extremely succinct proofs, and pushes all of the analysis into basically how many ones can be packed into a matrix and avoid this pattern. Okay, let me do one more example. This one is from enumerative combinatorics. So here we have a big permutation sigma and a little pattern pi, and we're interested in basically how many different sigmas avoid pi as a subpattern. So in this case, sigma does not avoid pi because 7410 is order isomorphic to 4321. Okay, if you just sorted the blue numbers on the left, you get the exact sequence here on the right. So right, order isomorphic. Yeah. Okay, so so Stanley and Wilf back in the 80s conjectured something independently along the lines of, if you counted the number of n permutations sigma that avoid a particular pi, then this should be just some singly exponential upper bound. It shouldn't be n log n, for example. 2 to the n log n. It took a while to prove this. So the first step was to connect it with a problem in this 0-1 matrix theory. So Stanley-Wilf conjecture is about the number of permutations, and the Ferretti-Heinau conjecture says that if you have a permutation pi, and p pi is kind of the 0-1 matrix representation of this permutation pi, then the number of ones that you can pack into a matrix and avoid this should be linear. Okay, and the Ferretti-Heinau conjecture was unproven for many years, and Lazar showed that before either of these two things were proven, he showed that the Ferretti-Heinau in fact implies Stanley-Wilf. So this created a certain incentive to prove the Ferretti-Heinau conjecture. And I can show this reduction here in the rest of the slide here. It's extremely succinct. It's very, very short. And then proving Ferretti-Heinau is a separate problem, and that's also not too complicated. Okay, so how do you prove this? So you say, let's say f of n is the number of these matrices in the Ferretti-Heinau conjecture that avoid this 0-1 matrix P pi. Okay. So what do? We were going to come up with a little recurrence relating f of n and f of 2 of n to n. So how are we going to do this? If I give you a 0-1 matrix here, you can always shrink it by a factor of 2 by doing the following. You take this, chop it up into 2x2 submatrices, and then you replace it with the OR of those bits. So if it's all 0, it stays 0. If there's any 1s in here, then it becomes a 1. Okay. So so we can bound the number of matrices of dimension 2n by saying, okay, well, we have only f of n different matrices of dimension n that we have to think about. If you believe the Ferretti-Heinau conjecture, then there's this many, some linear number of ones in the matrix. And each of the ones in this matrix here, if you invert this, could give rise to 15 different submatrices here, because you need a 1 somewhere, so it can't be all 0. Okay, and therefore you get that this recurrence holds. Okay, so if you assume that this exponent here is linear in n, then that means that the whole thing f of n is going to be some constant that depends only on pi. Okay. Good. Okay, so good. Okay, so you can sort of think of this 0-1 matrix theory as being like an ordered version of Turan theory. So what's Turan theory? Turan theory says we don't we care about graphs, but we don't care about any order that you impose on the vertices. Okay, so this is a pattern. You can think of it as a bipartite graph where the columns correspond to vertices, the rows correspond to vertices, and this is just the incidence matrix of the graph. Okay, and of course the columns are ordered and the rows are ordered. So you know, in an unordered sense, this is just a path of four edges, and in an ordered sense, you know, it's more complicated. Okay, so I'll just use a different exponential function here with a little tu to emphasize that it's Turan theory. So here in Turan theory, you just say, well, I have an n vertex graph. I want a packet full of edges and avoid some subgraph that looks like H, and there's no notion of order. Okay, so here's basically a very crude classification of Turan theory. This is all more or less resolved by the 50s, 60s, or 90s, depending on when you want to be particular about things. Yeah, if your H that you're trying to avoid is not bipartite, then you can put n squared edges. It's not very hard to do that. You just a complete bipartite graph will avoid that. Okay, and you can even get very precise about the leading constant in terms of the chromatic number of H and all of that. Okay, so the more interesting case is the thing that you're trying to avoid is bipartite. And here it's known that the external function is going to be bounded away from n and n squared. It's going to be, you know, some polynomial whose exponent is neither 1 nor 2, somewhere in between. There's some interesting special cases here. So if the thing you're trying to avoid is an even cycle, then you're basically talking about the girth conjecture. And this is conjectured to be, you know, roughly n to the 1 plus 1 over k, where 2k is the length of the cycle that you're avoiding, and it's, you know, it's been proven for a few cases, but it's still open. Okay, so, you know, there's no easy problems left in Turan theory. And another special case is the Zerankiewicz problem, which is the thing you're avoiding is a t by t complete graph, and here the conjectured bound is 2 to the minus 1 over t, and it's only been confirmed in a couple of cases, so it's also, you know, a hard problem. So except for these two, I don't really know of any natural, you know, things that you could look at in this category that are sort of not terribly hard. And then the third category here is when the thing that you're trying to avoid is a forest. Okay, so it's also bipartite, but it's a forest. And here showing a linear upper bound is extremely easy. And you can even get really sharp upper bounds in the leading constant as well. So this is, you know, a brief overview of the classification in Turan theory. So in the zero and matrix theory, this doesn't have an analog because zero and matrices are sort of forcing you to look at bipartite graphs. So we're only talking about these and these, essentially. Okay. So Pettie and Heinel had this nice paper, and at the end of the paper, they made a bunch of conjectures connecting the ordered theory and the unordered theory. Okay, so if P is a zero in pattern, GP is the corresponding unordered graph. Okay, so their first conjecture, this was used to prove Stanley-Wilf, is if P happens to be a permutation, then the graph is a matching, and their external functions should both be linear. Okay, and this turned out to be true, of course. But then they made several more conjectures. So the second conjecture was, it turns out these external functions can be different, but they thought that they can't be too different. They were like, conjecture 2, for any pattern P, the unordered and ordered external function should never differ by more than a log n factor. Okay, and they immediately doubted this. And in the very next sentence, they said, well, it would be interesting if it were at least true for the acyclic graphs / matrices P. So if P corresponds to a tree or a forest, then is its external function always bounded by n log n? Okay. So this one turned out to be true. This is Marcus and Tardosh's proof of Stanley-Wilf. Hock and Tardosh show that this second conjecture is like extremely wrong. Okay, so you can come up with a graph where it's a 2k cycle, and the ordered version of the graph has an external function that's n to the 4/3, and you can make k as big as you want. So in the Turan world, you can force the external function to get arbitrarily close to linear, but here it just never gets smaller than n to the 4/3, so there's an n to the 1/3 gap. Okay, and how do you construct one of these things? There's lots of different ways to do it, but one way you can do it is just write out a cycle And when you're writing it out as a 0 matrix, just always turn right. You know, so if you put a 1 here and a 1 here, and you turn right, 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 and you come back to where you started, then this will satisfy this end of the 4/3 lower bound. Okay. Yeah. Okay, so 2010, I refuted the third conjecture just barely. Came up with an example where you could squeeze out, you know, a little log n factor at the end. And then last year with Gabor, we showed a proper refutation where we can basically, you know, for any t that you want, we can come up with a pattern that gives you roughly log n t's, t log n factors. Okay, and this is a more, I say, solid refutation. Okay, but even before that was refuted, Hock and Tardosh in a separate paper came up with a much more robust version of the conjecture 3. So what they thought was this n log n is very implausible, but here's a much more plausible replacement for conjecture 3, which is if you have an acyclic pattern, then the extremal function should never be larger than n times some polylog factor that depends on p. Okay, and the strong version of their conjecture, they even nailed down the exponent. They said it should definitely not be more than p minus 3. P, where p, this thing is the number of ones in the pattern p. Okay, so why did they come up with that p minus 3 thing? So basically, if you have 3 ones, it's linear, so that's why the 3 is there. But why is this thing here? So they basically came up with some reductions that show that adding a 1 to a 0, 1 pattern in many circumstances only adds a log n factor. So if you have a pattern p prime and you stick a 1 in the last column, you create a new column at the end and stick 1, 1 in there, that can only increase the external function by a log n factor at most. Okay. And they gave another reduction saying, you know, if you have ones that are sort of in this pattern here, and you splice a new column in between them and you stick a 1 there, then that can also only increase things by a log n factor. Okay, and you can use these two reductions to prove lots of things are, you know, n times polylog n. So the pattern on the top left, you just perform the first reduction and you peel off the ones from the end 1 by 1 until you left with nothing very much at the end. And you can perform reductions on something like looks like this. It's a little trickier. So for this one here, the first thing you have to do is actually stick a new 1 into the middle, which only increases its extremal function. But then you can apply reduction B to splice out this column, and it, you know, shrinks there. And then you'll apply B again to splice out this column, and you get something that looks like this. And now you can apply reduction A to columns or rows. It doesn't really matter. So now you can apply column reduction A to the first row and take this off. And once you do that, you're left with a pattern that happens to be linear. So we're done. Okay. And the whole, you know, chain of things here is every time you apply A or B, you lose a log n factor. So we have 3 log n factors at the end. Okay. Yeah, but these reductions aren't universal. They don't let you, you know, generate any matrix you want. There's lots of, you know, matrices that you can't analyze in this fashion. Okay. So, but they basically show that these reductions are enough to nail down a whole bunch of things. So every weight 4 pattern you can analyze directly with these 2 reductions. Every weight 5 pattern you can analyze with these 2 reductions. So these are more, you know, interesting versions of the weight 5 patterns here. And you can get nearly all weight 6 patterns as well. Okay, but not all of them. Okay, so there's 2 exceptions. And these are the 2 exceptions that you can't get at with pocket reductions. S0 and S1. And the best upper bound that we have on these are much bigger than n times polylog n. They're, you know, n times something exponential in root log n, or n times something exponential in log n to the 2/3. Okay, so how did they come up with these bounds here? So Karandi et al. Basically came up with a way to analyze patterns in terms of what they call their degeneracy. And they say that a pattern is degenerate if you can cut a line through it, and the pattern above the line and the pattern below the line only have 1 column non-zero column in common. So every other column is entirely, you know, if there's ones up here, then it's all zeros below. If it has any ones down here, it's all zeros above. Okay. So S0, you can obviously cut in this way. You can cut any, you know, anywhere and do that. For S1, you have to cut here. Okay. So they'll call it class S degenerate essentially if when you cut it, both of these two things are inductively class S-1 degenerate. Okay, so S1 is class 2 degenerate because if you cut it here, and then the remaining matrix, you can cut it here and decompose all of its rows by cuttings. Okay, so what's the upshot here? If you're degenerate for any constant S, then your exponential function is n to the 1 plus little of 1, but you know the exact S really does affect what's going on here next. Okay, so all right, so this is the best upper bound on these matrices here. Okay, so yeah, so our main result is a refutation of the Pock-Tardush conjecture, and it turns out that they certainly would be surprised by this because they didn't think their analysis was tight, but our lower bound here actually matches the upper bound on S0, so their analysis is tight up to the constant and the exponent, and it turns out that you know, whatever they were doing was you know more or less precisely to work at the correct thing. Okay. Okay, so we also have some additional results. We actually got started with this problem first, and then we realized that the Pock-Tardush refutation sort of followed as a corollary of this. But we were interested in analyzing matrices that avoided these types of patterns, these type of alternating two-row patterns. And here we got some very sharp, you know, upper and lower bounds on the exponential function of these two-row patterns here. So it's precisely log n over log n to the t, where there's t plus 1 alternating ones. Okay. And it turns out that the lower bound construction for these and the lower bound construction for the previous ones is essentially the same, it's just parameterized differently. And I can show you briefly how the construction works. Okay, so the results in this area, I would say they take forever to find, and then when you find them, you can usually explain them on 1 or 2 slides. So they're super simple after you find them, but not before. Okay, so I call this the good, the bad, and the ugly construction. Gabor does not call it this. He calls it some other movie reference. But I'll get to why it's called that. Okay. So okay, so we have 2 integers, parameterized by 2 integers m and h. And we're going to create a matrix, and the rows of the matrix are pairs, S and R, where S is one of these numbers less than m, and R is a vector of these numbers. Okay. H is always the length of the vectors. That's all it is. Okay, the columns are indexed by these vectors of numbers and also a bit vector numbers. And when we create this matrix, we need to choose an order, of course, and the order is always going to be lexicographic. Okay. So we want this matrix to be square ultimately. So these 2 things should have the same size. And therefore we want m to be exactly 2 to the h. Okay. So when you set m to be 2 to the h, then the dimensions of the matrix is roughly 2 to the h squared. H is square root of log n, and this is where the square root of log n is going to show up. Okay. So what's the rule for deciding, where to put the ones in this matrix? So we have, a particular row SR and a particular column CI, and we will stick a 1 there if you can express R as CI plus this. So you take all the 1s in the 0, 1 matrix and the 0, 1 vector I, place them with S's, and add them to C. Okay, and this is the rule. So, why good, the bad, and the ugly? So this is the good. Who knows where? Did anyone see the movie? You'll get this, I guess.
Looks like there's a thing.
Yeah, that's it.
Yeah,
Wah, wah, wah.
yeah, that's it.
Okay.
You sing better than I do. I'm hurt.
Okay, so they're trying to find the money in the grave. And the good knows the name on the grave. The name on the grave is S. Okay. The ugly, and then the bad, knows the location of the grave. The location of the grave is I. Okay. And when they get together, then they find them. This is the happy, mostly happy. Okay. So yeah, that's the construction. Okay, so I can maybe try to explain why this construction avoids the pattern S0 and S1. Okay, so this is the pattern S0, and I'll get to analyzing that in a second. But for now, we should just think about what's going on with one little row of this pattern in terms of the construction, what it tells you. So the row, let's say, is SR, and the columns, we have two columns, C0, I0, and C1, I1. Okay, so what does this mean? These two ones mean that I can express R in two different ways. I can express it as some offset of the C0 vector and some other offset of the C1 vector. So the difference between C0 and C1 is going to be S times the difference between I0 and I1. Okay. Now the lexicographic order here. Well, first of all, I0 and I1 are bit vectors, so this difference here is some -101 vector, and the lexicographic order says that the first non-zero, because this column comes after this column, the first non-zero here can't be -1. So the first non-zero has to be 1, and therefore the first non-zero in this vector here has to be an S. Okay. So once we have this fact here, now we can try to analyze all three rows of S0 altogether. So the way to look at this is you have these three rows, and we're going to call the distance between the first one in the row and the last one in the row in the pattern here X for the middle one and Y and Z for the others. Okay. So the first thing that you can figure out here is that the S's, especially since we're doing this lexicographically, the S's are in non-decreasing order, and they actually have to be strictly in increasing order because of what's going on in the first and the third column here. Okay, so that forces the three S values here to be distinct in increasing order. And the second thing you can notice by inspection is X is bigger than Y and Z. But Y plus Z is actually bigger than X. Okay, so good. Okay, so now you can write out X, Y, and Z. Okay, so from the previous slide stuff, X, Y, and Z are going to be of this form here, where it's some vector that starts with S1, or whose first non-zero is S1, some vector whose first non-zero is S0, and for some vectors whose first non-zero is S2. Okay, so X at some point its first non-zero is an S1. Okay, so Z is smaller than X, but S2 is bigger than S1. So what that means is that the first non-zero position of Z has to come after the first non-zero position of X, because S2 in this coordinate is bigger than S1 in that coordinate, so cannot come at the same place or earlier. And then Y. Well, S0 is less than S1, so it may be the case that S0, the first non-zero here, which is S0, occurs in the same position as the S1, or it could appear afterwards, but it does not appear. Okay, so now we need, so Y and Z are less than X, and we need the sum here, Y and Z, to be greater than X. So that is a problem. You cannot add up these two vectors here and get something greater than this vector here. There's no carries. Okay, so that's our contradiction. Okay, therefore this pattern can't exist in the matrix. Okay, and a similar argument, works for other patterns. Any questions on this? Okay, so this is the upshot. And the best that we can do to, once you start messing around with this, you're like, well, if I can get 2 to the square root of log n, maybe I can go back to the Karandi type, bounds and say, maybe I can get 2 to the log n to the 2/3 if I do something clever, or 2 to the log n to the 3/4. That was one of their, functions. And we couldn't do any of that. All we could do is basically boost the constant in the exponent to be anything that we wanted. So if you want this constant to be 1000, yeah, we can come up with a particular pattern S0, the 1000 version that that hits that particular exponent function. And the way you do this is in the interior rows of S0, you just kind of alternate between the first and third rows a whole bunch of times instead of doing it just once. Okay. And there's some other, modifications to the construction you have to do with sort of generalizations of Barron's construction, blah, blah, blah. But this is basically as big as we can get with this type of construction. Okay, so when we refuted the Pak-Tardos conjecture, it was about 0 matrices, and it also refutes a bunch of other conjectures that were kind of built on top of it, or were generalizations of it, or in some sense, talking about the same thing, but maybe in a different way. So Ferretti et al. Did a similar conjecture for ordered hypergraphs. So that's also refuted. Shapira and Euster came up with sort of an extremal theory of tournaments, where you supplement tournaments with additional edges, and some idea of pattern avoidance there. And their conjecture is also refuted. They showed that their conjecture was equivalent to Pak-Tardos. And then later on, this took a little bit more work, but there's sort of a theory of edge-ordered graphs. All the things that we studied were basically vertex-ordered. The vertices have an order, but the edges themselves don't really have an order. You could come up with the theory of vertex-ordered graphs. They made a conjecture similar to Pak-Tardos, which is also refuted. And with the student, we showed there was another conjecture in the original Pak-Tardos conjecture is also false. And the idea here is, when you take your subgraph H that you're avoiding, you could pick, like, let's say the most advantageous P with the smallest extremal function that's an ordered version of H. And they thought that in this particular case, you could always find some version P of H where the extremal function is differed by log n factor. And in fact, you can make this not just log n, but any polylog you want. Okay. So I'll start off, that's basically the end of the technical, talk. I'm just going to talk about future, conjectures and open problems and stuff like this. So, there's a correspondence between Turan theory and ordered Turan theory, which is these forbidden 0 matrices. And most of the action is in the acyclic universe, which no one in the Turan theory thought was interesting, but has become sort of the most interesting part of this, 0 matrix theory. So if you have an acyclic H and you create an ordered version of it, there's a whole hierarchy of possible extremal functions you can get. You can get linear ones. So you can create permutations. These are all linear. You can have these monotone patterns. These are all linear. The next level up is the light patterns. These correspond roughly to Davenport-Chinsel sequences and those type of things. And these patterns all have exactly 1, 1 in each column. And whenever your pattern looks like that, you're going to have some quasi-linear upper bound where it's n times some function of the inverse Ackermann function, alpha here. Above this level, you have the n polylog n patterns, and there's lots of examples there. And we have this new stratum here, which is n times 2 to the square root of log n. And of course, we don't really know, is there another category that you need? Can you get polynomial, lower bounds for acyclic matrices? Maybe you can get n to the 1.1 or something like that. Okay, so yeah, so the main open problem is prove any upper bound, universal upper bound on an acyclic pattern. Okay, so for example, if you can say for any acyclic pattern, the upper bound is always n to the 1.99, that would be a new theorem. No one knows this, if this is true. And maybe a more specific thing, given these Courandi degeneracy upper bounds, is try to go from square root of log n just all the a little bit higher up to log n to the 2/3, let's say, from the lower bound perspective. Okay, so we have a conjecture here that basically our upper bounds are tight. You can't beat them. And this is the strong version. The weak version is that you can't get anything that's a proper nonlinear polynomial, n to the 1.1 or something like that. Okay. So here's another interesting problem, which is the dealing with light patterns here. So light patterns basically correspond to Davenport-Schinzel sequences, and they're really understood very well when they have two rows, exactly two rows. So we have these that sort of capture the lower envelope of line segments, and you get n times inverse Ackermann. If you've never seen the inverse Ackermann function, I guess I could define it at this point. So here's a succinct definition. So whenever you have a decreasing function f, you can have a version of it f star, which is the number of times you have to apply f to get down to a constant. Okay, so the inverse Ackermann function can be defined as the number of stars you need so that log with that many stars of n is a constant. Okay, and yeah, so when you have two rows here, the extremal functions increase each time, but not terrifically quickly. Okay, and this has all been sorted out basically. Okay, so a light pattern is one that has 1, 1 in each column, and when you have 1, 1 in each column, you're basically always going to get an extremal function roughly of this form from this set here, and sometimes they're linear, and sometimes they look just like the corresponding Davenport-Schinzel, example up here. And knowing when they're linear and when they're not linear seems to be like a good classification question. Okay, so a very tricky problem is just to say classify the set of all patterns that happen to be linear. Okay, and this is tricky. It definitely cannot be characterized as a pattern is linear only if it avoids a certain sub pattern of a certain type. So you're not going to come up with any like characterization of planar graphs that say you're planar if you don't have a K5 or a K33, just some list of forbidden subpatterns. Okay, you're not going to see that. This is won't work. But this might have such a characterization. So if you want to characterize a set of light patterns that happen to be linear, then it's certainly consistent with what we know that the only way to be nonlinear is to have one of these two patterns or their reflections. Okay, so this would be an interesting explanation for the class of light linear matrix. All right, thank you.
Shall I place 38 from in?
If you want. So I give this talk in front of Sergei Fomin, who's Russian. And he said at the end of the talk, he said, that talk was very, and then he looked for the right word, Hungarian.
You have to explain. Sergei Fermin is a very distinguished algebraic combinatorist.
Yeah.
Best known, very famous for vertex algebras.
But he liked no, sure.
So how long did you work? How long were you in Budapest? I'm amazed. I'm amazed that you could get started and do this like in a week.
Oh, we obviously you saw the citations. We've been working on this. I've been working on this since like 2010.
I remember.
And he's been working on this at least since 2003 or 4 or something.
I was say I remember lots about Davenport.
Yeah. So we hit the ground running, obviously.
Okay, so it wasn't just like looked up.
No. I was there like less than 2 weeks, I think.
Okay, wow.
And then then we just worked it out over the next few years, I guess.
Wow, that's impressive.
Yeah.
All right. Do any of you guys have questions? Even sociological.
Yeah.
How did you do that?
Yeah, sort of. So for the construction with like the matrix that's that's parameterized by like the columns and or like the two parameters, the good, bad, and the ugly.
Yeah,
How do you approach like to do that? Why that thing?
Yeah.
Like, is there like an intuition or motivation, even like in hindsight?
even in hindsight. No, there's a version of it that, I mean, so it started off real slow, before it was like, you know,
Right, that and it seems like there's some algebraic structure built into that.
yeah. Gabor was just looking at the very simplest matrix that, you know, we didn't know how to classify. And he was like, you know, well, if you wanted to come up with a zero matrix that avoided this, what would it have to look like? You know? And then he came up with a version that it was sort of an ad hoc kind of construction, just for this one right here. And it had certain features that were easier to generalize, let's say, than previous constructions. Okay, so then the next step is to try to get from here to sort of, you know, an arbitrary number of alternation. And the construction here had, you know, let's see, we came up with had this type of external function here, and T is built into the construction itself. I mean, you sort of have these vectors, you chop them up into T blocks, and you say, I'm going to do something in this block, and something in this block, and something in this block, and so forth.
Yeah.
And that works great. And then I was messing around with it, and it's like, you know what? These things, you know, the S0 pattern, which is like, you know, like this, these points here, these things would avoid these constructions for every T. Okay, so if now it's just a matter of choosing, you know, sort of the maximal T that you can in this construction, and T squared log n balances everything out. And then you can simplify that a little bit to make it look like the one I showed on the slide, but basically it comes from this sort of generalized block construction here. So yeah, it starts off real slow and it's laborious at first, you know, but then, yeah, you get to the end, you're like, that doesn't make sense. You would never come up with that. I mean, I wouldn't come up with that straight away.
Are there any computer aided proofs or like this back algebra mechanism using this algorithm?
Any computer aided proofs? Ew. There should be. there should be. Yeah, there's a few unreadable proofs that I think really would benefit from some computer assistance. But no one's done brute force. I mean, no, I don't think anyone's done kind of brute force searches or things like that.
Yeah, for example, suppose you want to ask a question rather than how to forbid the structure. What is the so as you increase the number of ones, what is the max the minimum density of this forbidden structure you're gonna see as you increase it? Like have people done my like this back algebra might be useful for this kind of problem, like in the dance.
I don't know any work along these lines.
Okay.
Yeah.
Like this Turan theory for the graphs that we used that algebra to study. That's pretty much just solving some SDP and
Yes.
simplifying something.
Yeah. All right. Oh, I should make an announcement. Well, first of all, let's thank Seth. Many of my kids' jokes are connected to Seth. And one of the family jokes was.
Wait. Stop recording.
Oh, yes.